2-3 days you have not attended LICA, but you have attended other classes during LICA time. Okay. Now today's class, let me start. Previous class we have discussed about what is that various, I mean unit 3 we were discussing, no? Just I have started unit 3. Unit 3, linear and non-linear applications of op-amp. These linear and non-linear applications of op-amp, we have seen op-amp used as inverting and non-inverting amplifier, then integrator and differentiator, and difference amplifier, instrumentation amplifier. Like that I have given a lot of introduction, right? So therefore just I will show these slides just to recollect and recap, and after that today we are going to learn a few more new things, right? Now coming to op-amp, why op-amp is not used in open loop mode I have mentioned, right? Because of its large gain. And in closed loop mode only it has many applications I have mentioned previous classes. Then general purpose op-amp 741C and its range, all that we have seen. And here we have I have mentioned that these two are the two assumptions, realistic simplifying assumptions that we use in op-amps. Okay, first one is zero input current. How is it possible to have zero input current? That means op-amp has, an ideal op-amp has infinite input impedance. Input impedance of an op-amp, input impedance of op-amp is infinity, right? For an ideal op-amp. That means when there is a short circuit, maximum current flows. That means resistance is zero. When there is open circuit, resistance is infinity, and a current will be zero, right? So now the input impedance of the op-amp is infinity. Therefore, current that is flowing at the input terminals is zero, right? Between these input inverting and non-inverting inputs, right? So zero input current, the current drawn by either of the input terminals, inverting and non-inverting terminals, is zero. This is one basic assumption we have to keep in mind, right? The current drawn by either of the input terminals, that is inverting and non-inverting input terminals, is zero, because at the input of op-amp it is like open circuit. Input impedance is infinity, therefore it is like open circuit. So either inverting or non-inverting input terminals, they draw zero current because input is like open circuit. Input impedance is very high. That is first assumption. Then the second one is virtual ground. It is about virtual ground. That means the differential input voltage, VD. So that means here the difference between these two input voltages. Okay, so the differential input voltage VD between the non-inverting and inverting terminals is zero, right? See, it is like this branch is not drawing any current, and this terminal is also not drawing any current. And not only that, the difference between the input voltages, voltage between input terminals, inverting and non-inverting input terminals, is zero. That's why where do we have zero potential? Means at a ground potential, otherwise at reference potential or ground terminal. That's why we also call this as virtual ground concept. This is called virtual ground concept. That means the voltage at the non-inverting input terminal of op-amp can be assumed to be equal to the voltage at inverting input terminal, right? That means their difference is zero. Means what? Voltage at inverting input terminal is equal to the voltage at non-inverting input terminal because of this concept called virtual ground concept. Otherwise, we can say that the differential input voltage is 0. Differential input voltage is 0 means what? Here at inverting input terminal 1 volt is there. At non-inverting input terminal also same 1 volt will be there and difference will be 0. Right? So that we call it as virtual ground. Right? Virtual ground. This means that the differential input voltage VD between the non-inverting and inverting input terminals is 0. That is, the voltage at non-inverting input terminal is assumed to be equal to the voltage at inverting input terminal, right? So this is the virtual ground concept. Many times in almost all the designs of our circuits using op amp, we'll come across this term again and again. So we'll move forward with this concept in mind. Okay, then we came to know that op amp is used in closed loop configuration. How is it possible to have closed loop configuration? Means feedback. Only with feedback it is possible to have closed loop configuration. And what type of feedback? It is negative feedback, right? So how do you say that it is negative feedback? Output is fed back to the input at inverting input terminal. Then you say it is negative feedback. Why we go for why we go for negative feedback means to control gain of the amplifier. Okay, then we have seen inverting amplifier. I think you have taken this circuit diagram of inverting amplifier. Okay, here we are just showing all offset adjustments also. Actually, in our future discussions, for simplicity's sake, we do not indicate all this, right? Of course, it depends on others. Okay, our Ramakanthan Gaikwad textbook, he always draws all circuit diagrams like this. Okay, if you like this type of diagram, you please draw like this, right? Sometimes this plus VCC and minus VEE and potentiometer between pin numbers 1 and 5, that is offset null adjustments, all these we will not show, right? For simplicity's sake. Whether we show it or not, all these adjustments will be there. So what I ask you to do is, as you wish, right? In the examination, you will be having 3 hours time. Here we have to cover our syllabus. So the already covered points like plus VCC, minus VEE, all these are implied. Whether we indicate or not, we have to give these voltages. At the same time, pin number 1 and pin number 5, these are offset null points. Okay, so these offset null adjustment, if you like, you just draw and show so that your circuit will be looking good in the examination point of view. But for simplicity's sake, what we do is always we eliminate. Eliminate means we skip this, we don't draw. Simply 2 inputs and 1 output we draw. Okay, so you please keep in mind whenever you draw op amp, if you indicate pin number 7 plus VCC, pin number 4 minus VEE, pin number 1 and 5 between what is that, potentiometer, and its variable terminal will be at minus VEE. Like that, if you connect, it will be more effective. Okay, now this is the operational amplifier connected in inverting mode. Why we call it as it is connected in inverting mode means we have given input at the inverting input terminal of the op amp. Okay, then we are talking about closed loop configuration. Therefore, a portion of output, that means output is fed back to the input, inverting input, through a resistor called feedback resistor, right? Through a resistor called feedback resistor. Of course, here you can have some feedback elements. It may be a resistor, it may be 2 resistors, it may be resistors in series, resistors in parallel, or a capacitor, whatever you want. There will be some feedback network. So here we are just showing one feedback resistor here, right? Now, at the input, of course, this is internal resistance along with the internal resistance of the source. Otherwise, we say some through some resistance, current limiting resistance, we say through some resistance we apply voltage. So when you remove this voltage source and when you connect it to the non-inverting input terminal, this terminal you will be grounding. Okay, right. Now this is at the input, and other input, inverting input, this is about inverting input. Yet non-inverting input, just some what is that, some null adjustment values will be connecting here, some resistor here. So you need not think much about it. Is almost like ground only. So if there is any adjustments, offset adjustments, we have that. Sometimes what we do is some compensation resistor, like these two parallel resistance, whatever you have, that value we connect here. Otherwise all the resistors whatever we have. So we'll come across this point in future, some other point. Now let us treat it as a ground like. Now non-inverting input terminal is grounded, and inverting input terminal we have given voltage source, and a feedback resistor is connected, and output is taken across a load resistor, and between offset null points a resistor or potentiometer variable resistor is connected. So for such an arrangement we can express what is V0. Okay, so this current is equal to this current, otherwise current entering equal to leaving, all that we can write, and otherwise this branch current is equal to this branch current. So from that we can just write what is this V0. Okay, we'll come to this expression. So this is what about the circuit diagram. Have you noted this circuit diagram in the previous classes? Previous class?
Yes, ma'am.
Yes, okay then.
Yes, ma'am.
Good. Right. So this is what about the inverting amplifier. Now, the equation for voltage gain we can easily write. So that is, you can write Ohm's law, right? That is V0 by feedback resistance, that branch current is equal to V in by R1. I'll show you this. This branch current is equal to this branch current. Otherwise, this branch current is equal to this branch current magnitude. Sign means if one is entering, other one is leaving. If this is entering, other one is leaving. Actually, output is fed back to the input, right? So therefore, this is I. Actually, what happens means at the input terminal, it is grounded. Pin 3 is grounded. Therefore, it is also like grounded. Therefore, current whatever we are getting from here will be traveling through this I only. That means a current that is through RF will be same here. So we can write this as V out by RF. V out, this is V out by RF, this one, right? From here, if we consider this as a reference, right? V out by RF is equal to minus V in by R1, because it is in the other direction. So minus V in by R1. So this branch current is equal to this branch current. So when you write like this, you take V out is equal to minus V in by R1 into RF. It is nothing but voltage gain is equal, V out is equal to minus RF by R1 into V in. Otherwise we say AV is equal to V out by V in, which is equal to minus RF by R1. AV is equal to minus RF by R1. So like that we can write voltage gain for this what is this, inverting amplifier. V0 by V in is equal to ratio of these two resistors. So if we see the what is that properties of this ideal inverting amplifier, output is inverted with respect to input. It is an inverting amplifier, therefore you know that if input is like this, output will be magnified and at the same time opposite in phase. That we have proved several times. And that voltage gain is independent of open loop voltage gain. That means you see voltage gain AV is equal to RF by R1. That means it is the ratio of two resistances only. That means by selecting the values of resistors R1 and RF, R1 and RF, you can obtain whatever gain you want. You can design an inverting amplifier with the required gain, right? Voltage gain depends on the ratio of two resistances only. So that is another advantage. That means closed loop voltage gain doesn't depend on open loop voltage gain. We know that open loop voltage gain is in the order of 2 lakhs like that. So it is very, very high, and practically that much high voltage gain is not required for us. So we say that the voltage gain for closed loop configuration is independent of open loop voltage gain, and it is the ratio of RF by R1. So these are some, what is that? If RF is greater than R1, if RF is less than R1, what will happen? If RF is equal to R1, what will happen? All that we can explain. Okay. Similarly, if RF equal to R1, what will happen? Voltage gain is equal to RF equal to R1. Voltage gain is equal to minus of 1. That means if RF equal to R1, V out is equal to minus V in. V out is equal to minus V in. That means if you give input voltage like this, you will get output voltage like this. No amplification, just phase shifting is taking place. So we also call it as a phase inverter or phase shifter. Phase inverter we say. Then closed loop, it is of course closed loop gain we can indicate with ACL like that. Okay. Then non-inverting amplifier, let us say, right? Let us say non-inverting amplifier. Here voltage gain is always greater than 1. Previous case, it depends on the ratio. It may be, what is that? Here we have. If both are equal, then we say it is 1. Unequal may be greater than 1 or less than 1. Whereas in non-inverting amplifier case, we will have gain is equal to 1 plus RF by R1. So because we have 1 plus something, voltage gain is always greater than 1, right? That is one point we have to remember. Then there is no, what is that, phase shift, right? It is same for both input and both the DC. And then output voltage gain depends on is independent of open loop gain, like in the previous case, and the voltage gain can be controlled by using the value of resistors RF and R1. Today all this of course we have discussed lightly in the previous class, I think, right? Today we are going to learn about inverting amplifier, which is used as a summing amplifier, right? So actually we are talking about only single input. We will see today summing amplifier, right? Now that is about inverting and non-inverting amplifier. Just now I have seen here, similar to the previous case. If you write these currents V0 by V in ratio, you will get 1 plus RF by R1. I will show you here. Closed loop gain is equal to V out by V in. Closed loop gain is equal to V out by V in, right? V in. Closed loop gain V0 is equal to closed loop gain is equal to V0 by V in. So that is what I have written. Now we'll write what is V out and what is V in. What is V out? Let us see. V out is equal to, this is the feedback component. So V out is equal to, you just observe, this is like, what is that? This is at ground potential. Therefore, what happens means V out is, you just see, this other terminal is connected to the ground. That means V out is equal to IF into R1 plus RF, right? That means if you write this as feedback feedback current that is flowing through resistor is feedback resistor. So V out is equal to, and here it is like virtual ground. Therefore, of course, here you know that it is open, and therefore current doesn't flow this side. So the same IF will be flowing through this. Okay. So therefore, V out is equal to IF into RF plus R1. So IF into R1 plus RF. This is V out. Then what is V in? V in is equal to, what is V in? V in is equal to actually this value, right? Here we do not know how much we give. Therefore, in other words, we can say V in is equal to, you can say, whatever potential we have here, the same will be at the other input terminal, because the difference between these two is 0. Otherwise, we say that due to virtual ground, whatever voltage we have the same voltage here. So therefore, whatever voltage at this point, this voltage only, no? So whatever voltage we get here, same voltage we can assume here because of virtual ground concept. That means from here to here, what is the voltage means? It is, what is that? Voltage drop across RF. Therefore, RF, what is that? RF, IF, you can say. So IF, RF is the voltage drop across this resistor. V is equal to IR. Okay, so this is the voltage drop across this, and this is the total voltage drop V naught, and therefore you can just further simplify this. You will get IF cancelled and R1 by RF plus 1. So that is 1 plus R1 by RF is the closed loop gain. Closed loop gain for your non-inverting amplifier, right? So here onwards, whenever we say inverting amplifier, it is what is that? Voltage gain is equal to how much? Minus RF by R1. And for this non-inverting amplifier, it is 1 plus R1 by RF. Okay, so that is the difference. And when you do this differential amplifier, similar to that, we will get output expression like this. That means minus of RF by R1 into difference of these two voltages, right? Difference of these two voltages. Okay, now let us just compare. When you are asked to discuss about inverting and non-inverting amplifiers, ideal inverting and non-inverting amplifiers, though you draw the previous circuits and these circuits and these explanations, these points you write, once again at the end, if you draw table like this, it will be more impressive and you can get a good impression from your examiner, right? So voltage gain is minus RF by R1, we can say minus voltage gain is minus RF by R1, and then here voltage gain is 1 plus RF by R1, and output is inverted with respect to input, and here no phase shift. Then voltage gain can be what is that? Greater than unity. Of course, can be adjusted as greater than or equal to or less than any value because of the resistor values. And here it is always greater than unity because it is 1 plus. Then input impedance will be, here it will be very large, and here it is equal to R1, right? Just simple same things what we have discussed, we have tabulated, that's all. Now in today's class, we are up to that we have discussed in the previous class. Today's class we are going to discuss about new things. That is, first thing is AC amplifier. Okay, we know that our op amp can be used for both DC amplification as well as AC amplification, right? What the circuits what we have discussed till now, they are suitable for both, but still why I am using this AC amplifier means a slight modification is required. Okay, of course, even if you do not do that modification, no problem. In general, what we do is when you use this op amp, same operational amplifier, either in inverting mode or in non-inverting mode, as AC amplifier, we do connect a coupling capacitor. We generally connect a coupling capacitor. What is the purpose of this capacitor? For blocking DC. In order to block DC, a coupling capacitor is required. So now let's go back to the amplifier, maybe inverting or non-inverting. So I'll just show you one inverting amplifier, right? So here we have not mentioned whether it is AC or DC. It equally works for both AC and DC. So here if you are using this inverting amplifier for AC input, what you can do is you just connect one capacitor, coupling capacitor. Then what will happen if there is any DC component, that will be blocked and only AC will be allowed to reach the input terminal of the op amp, right? So that is the modification that you have to do. Remaining thing, everything is same. Similarly, that is inverting AC amplifier with inverting in inverting mode. Now AC amplifier in non-inverting mode means here you connect one capacitor, right? Just after the signal source, you connect one capacitor. So inverting op amp, both in both for AC amplification and also for DC amplification, both are same except one coupling capacitor. Always wherever we want to block DC, there we connect a capacitor. So that capacitor we call it as a blocking capacitor. So that blocking capacitor is connected. Remaining things, everything is same, right? So that is what about DC amplifiers and AC amplifiers, right? Today's class we are going to learn little deeper, that is summing amplifier, right? Summing amplifier. So this summing amplifier, let me take your attendance once, and also I stop this recording.